ancestors, yeah. So I'm looking 20 years into the future, seeing what went wrong. Okay, so I hit next page. Yep. Phone not ringing? Oh, okay. So, it looks like we have a function that will be continuous everywhere. We have a sum of really two guaranteed positive values. X squared is positive, 3 is positive. So you're never getting to a 0 on that. So there's no discontinuity in this graph. But we always want to check, at least in our minds. All right, so we can go to our derivative process. Let's rewrite it. You don't have to do it this way. I'm just opting to do it this way. The quotient rule works really nicely for this because of the constant on the top.
Should we write C and D?
Generally, yeah.
Just write C and D everywhere.
Yeah, just go through the rest of your packet and write C and D.
Except when it's not.
Except for when it's not, of course, yeah. You only really have to worry about it when it's not. So, well, I mean, in terms of verifying it. So if there's a point of discontinuity, you need to flesh out where that is. If it's continuous and differentiable everywhere, if you make that statement for me anyway, that's all I need.
If I can't do the first and sign, is it okay if I do C plus D?
I mean, I'll accept it, but of course I'm judging you for your inability to do an ampersand. Yeah.
All right, that's fine.
Yeah.
I like the plus sign.
I mean, if you can get over that, like.
Can't do the and sign.
They're hard.
All right, start on the right.
You can't draw one of those?
Go back, loop it over and under, and then out. The key is in this area over here.
Yeah.
That little
I don't like
transition.
it's like
You got to take the turn Y. Right? So that's really how.
I used to do that in elementary school, and I thought it was really cool.
And you were, and you, for the record, you still are, for the ability to do it. Every time I do it, I feel just awesome.
Write it like the G cup symbol? No.
I made it a little too round at the bottom, but it's still allowable.
No, I always do this. I use it.
It's like.
You see, it has a lot of qualities of 8. So if you're thinking 8 backwards, and then finish it up with a G,
It's like the G cup.
then you're pretty good.
I'll use it all the time.
Go back with the bird.
I do. I mean, if I go quickly, like, I mean, it comes out like this. So, I mean, it's clear I was not going for an 8 followed by a G here, but it got the job done. The one caution is you will lose your ability to make an uppercase script S
Why?
because of the whole brain thing.
Yeah, but the uppercase script S is not that great.
Yeah, it's not really that
It's
necessary.
kind of a D.
Because it's really just, it's very similar of a process, just in the reverse.
In script, like, doesn't look like it anyways.
Yeah, so
Yeah, so just toss it anyhow.
it's not a big wall.
Alright, so derivative.
Yeah, it's just like braille.
I suppose we should probably do that or something. So f prime. I usually do an ampersand tutorial way earlier in the course, so the fact that we got this far.
AP Calc, learning the things that matter.
Exactamundo. Learn how to make chili. Actually, I never really went over that. Never really. We didn't really get into it. You just learned how it could be delicious. Yeah. But again, I don't think many people got the full effect because you all missed the bag of shredded Mexican cheese blend
Oh my bad.
that was right next to it.
No, I saw it.
I don't.
Oh, what?
Or you just opted out, yeah.
I'm also.
It was right there.
I have an idea, and I think I should go along with it. So like, for for the rest of the year, once a month we should have like a food day where we bring food.
For
I'm not
the rest of the year.
sure.
I mean, there's merit to that idea. Yeah.
And watch Star Wars.
I would
That
accept
was
the
right.
worst grade. That'd be a stretch.
Except the worst case for
So with that. Yeah, 2 weeks. So bad grades.
Table the conversation for 2 weeks. And
No, last kid is
I have extra credit.
Someone.
I'm pretty sure I'm not allowed to do that unless it involves calculus in some way. I'm sure we can come up with a plan.
I'll totally do that.
You could calculate which board is the most siffiest.
How would
The
you
most
calculate that?
As we take related
I think it would have to be Bane, Darth Bane. When he created the rule of 2.
I'm concerned that if your belly's anything that much.
What do you define as like
I mean, you got to be very siffy.
What are we doing?
No, I know.
It transitioned into Star Wars stuff.
What specifically defines siffiness?
All right, so
What is the scale?
for my critical values,
No.
I know acceleration.
Sorry, I like to
Constant acceleration of acceleration. You have snap.
all right. Well, anyway, so that sounded like fun, but I guess we have to do this.
Oh, right.
Oh my God,
you're so
So for the critical values, you want to set the top equal to 0. Well, you're really setting your derivative equal to 0, but that's equivalent to setting just the numerator equal to 0. And you also want to set it equal to 1 over 0, which is equivalent to setting the denominator equal to 0. But because we've already talked about how x squared plus 3 is never going to get you 0, why would x squared plus 3 quantity squared give you a 0? So nothing here, but we do have a critical value of x equals 0. All right, so that's the first part and the unfortunately easy part. We then need the second derivative. So we need the derivative of this guy. So, quotient rule, a little baby chain rule mixed in there, nothing too crazy. So low D high, so that's going to be negative 12 x squared plus 3 squared minus the high, so minus negative 12x, so plus 12x. D low, so that's going to be the little baby chain rule there. So it's adorable. Over the denominator squared, and where we go, all that good stuff. So, barring any mistakes, entirely possible, but we do want to simplify this, not because I'm telling you to simplify it, but because it's, like we have to solve by setting equal to 0. But I mean, I suppose you could get it done just by setting equal to 0 and going after it like an animal, but you probably want to clean it up a little bit more first. I mean, just the thought. And cleaning it up doesn't involve, that's the good news, it will never involve expanding out the denominator. So that's important to realize, because I see that a lot, like this monstrous expression on the bottom, like, well, okay, so that cost you like 15 minutes and you didn't need to do it. And in fact, it worked against you. So don't do that. Also, distributing out the top may work against you, because I notice here that we have a common x squared plus 3 that can be factored out and canceled across the board. So let's do that. And anything else that can be pulled out, you want to pull it out, right? So, I mean, there's really not much left. I suppose I could pull out a 12. Is that going to advance the cause? I don't know. So at this point, you can go either way. But this part is much nicer, and this part, it really doesn't require any effort. If we're going to simplify now, it's probably going to happen through addition and subtraction. So we can distribute on the top only. Negative 12 x squared minus 36. And then we'll have Really, it's just multiplying these three things. So 12, 24, 48 x squared, so plus. Now, in the second derivative, so the second derivative test for concavity, we're not setting the second derivative equal to 0 and 1 over 0. It's just equal to 0. So that denominator is very quickly going to become irrelevant. Simplify the top even more. 36x squared minus 36 over x squared plus 3 cubed. You leave it like that if you want. That would be our second derivative. You can factor it more if you want, but you don't unless you have a reason to. All right? So we'll see if we have a reason to later on. But we do have to set it equal to 0. Which is the same as setting the top equal to 0. I can kill the 36's. So our solution would be x equals plus or minus 1. Now just bear in mind, so we tend to write it as plus or minus 1 for simplicity. You may see the absolute value of 1 as a solution also. All right, you could write it either way. This, I think, the plus or minus 1 is more meaningful, but sometimes they'll put critical value x equals absolute value of 1 as a multiple choice solution. So we want to be prepared for that also. All right. And you'll be like, well, that's clearly not it, and it ends up being the right answer.
But that is a negative 1. Like, I know that if you put negative 1 in an absolute value side, it would be 1, but you're not giving the person that chance to make it negative 1.
Right, but the absolute allows it to be positive or negative. Yeah.
Okay.
You're not giving it an opportunity. It wants to be negative, but you're not letting it. I understand that. That's a fair point.
Justice for negative.
So now that we have all this stuff, and again, we're going to go with this one. This is my possible point of inflection. Pospoi. We have 0 and plus or minus 1 as my important points in my sign chart, the one that they don't tell you that you need to make, but you need to know that you need to make. So x, negative infinity to negative 1, negative 1, negative 1 to 0, 0, 0 to 1, 1, and then 1 on to infinity. So we need f prime, f double prime, and conclusion. And then I need to attempt to draw lines. Okay. Kinda. Whatever. See, the line draw tool is letting me down here. Sufficient. Oh, that hurts so much. All right, so we need to work off of our first and second derivatives here, and there's no assumption allowed that you're able to use a calculator even for a question like this. Right? So you have to assume that even the complicated ones, you could be expected to do it without a calculator. All right? So that's a very sobering thought. Anyway, the good news is, if I look at my first derivative, I can get all my signs in one shot. Right? Second derivative, we need a little bit more effort, but the denominator has to be positive all the time, right? Because it's a quantity squared, so it's irrelevant. The numerator is going to drive the quality of our derivative, because if x is a negative number, the derivative is going to be a positive result because it's negative times positive. if the derivative is positive, if x is positive, then the derivative will be negative. Right? So we can go right across the board now and get all of those. So negative x gives us positive first derivative and vice versa. But it's those little relationships that you need to be able to identify, right? Because otherwise you're actually plugging in numbers. You're plugging in a -2. What does that give me? You plug it in the top and the bottom. You know, sometimes you got to plug in a fraction, and it's not fun. If you can avoid doing that, it's obviously a time saver, because I just got through 4 calculations without doing any calculations, right? Any real calculations anyway. So then we have the second derivative. The bottom also still going to be positive, even though it's raised to the third power. That's fine. The quantity contained, x squared plus 3, is always going to be positive, and positive cubed is positive. So denominator irrelevant. Now I just got to worry about the top. All right. So we want to think about what's going to happen here, and you can do it if you want. A good intermediate step would be to come up with the factors. So that's the same as 36 times x squared minus 1, but that goes to x plus 1, x minus 1. All right? The reason I'm doing that, it's coming, yeah, there it is. The reason I'm doing that is to really emphasize the idea that you can come up with these values without having to do the rote calculation, or at least oftentimes without having to do the rote calculation. All right? Just by thinking of the quality of the numbers. So the 36 is now irrelevant. That's the important piece. The part that was making the top hard is irrelevant because it's positive. All right, so I would want to think about what's happening in these factors here. So if I have a number less than -1, that's going to make this negative and this negative, right? So then negative times negative would be positive. If I have something in between -1 and 0, right? So like -0.5, positive, negative. So result would be negative. Between 0 and 1, so like 0.5, positive, negative, so still negative. And then something bigger than 1, everything's going to be positive, right? So you can confirm by putting simple numbers in. But again, you'd rather put the simple numbers into a simpler part of the expression, right? So you still have to draw the conclusion that the bottom's irrelevant, the 36 is irrelevant, and the only thing that's going to drive the type of number would be these two factors. All right, so if I put in a 2, both parts are going to be positive, and the overall result will be positive. All right. So conclusions: increasing, concave up, increasing, concave down. All right, changing concavity. That makes this a point of inflection. All right, didn't ask for it, but why not, right? For practice anyway, on a test. If it doesn't ask, don't tell me, because if you screw it up, I'm taking off. So concave down. All right, so here we have a change not in concavity, but we have a change between, change in slope, so increasing to decreasing. So it's going uphill followed by downhill, so it must be a relative max. Then we have decreasing. Saw that plus sign right in front of me and I just went for it. Decreasing and concave up. So again, change in concavity makes it a point of inflection. All right. Now, it doesn't ask us to do it here, but eventually we're going to get to a point where we'll have to come up with a sketch, but now we have a lot of information to help us come up with a sketch of the graph of the original function. Because I know that it's increasing, then decreasing, right, overall. And then we have 2 points of inflection. So maybe we're looking at something like kind of like a normal curve. it's continuous everywhere, the original function, right? It goes from, it's increasing to decreasing, so increasing to decreasing. We have concave up, down, up. It could look something like this, all right? And that would be all I would need from you. Nothing on a graph, no scale, no axes labeled, no points plotted or anything like that. Draw a sketch of what you think this function would look like based off of the given sign chart, all right? So sometimes I'll even give you the sign chart, all right? Or at least elements from the sign chart, and you can come up with the graph. But this is kind of the gateway to getting us to that moment, all right? All right, so, oh, look at that. Good looking solution. So why don't you try number 2 for homework. It's a good looking problem. All right, I set up the domain so that you don't have to worry about discontinuity in the original function, because tangent is undefined at negative pi over 2 and pi over 2. But the parentheses are telling us that we're excluding those values. So the discontinuity would be irrelevant. So it may be a little bit easier than it's easier than it seems initially. I mean, it's still going to be work, but not insane work that it might seem initially. There you have it. 85. I think it was the next circled one because I deleted all the pages that weren't relevant. Hopefully I only deleted the irrelevant ones. It would help to look at the directions. Intervals where the function is concave upward and concave downward, and identify any extrema. Now, if it's only asking for concavity, then there's a case to be made that maybe you don't need to do a full-blown sign chart, but it's asking for extrema too, so you might as well. Now, this one's telling us to start at negative pi over 2, go to positive pi over 2, but don't include those endpoints, which is good because those are the only places in this graph where the function would be undefined. So we don't have to worry about that. That's good. So we don't have to worry about any kind of discontinuity. Although we don't have to worry about it. I don't know. Maybe we do want to worry about it because discontinuities work their way into the sign chart. They give you, kind of right off the bat, a value to put into your sign chart. Sometimes it's more work, but at least it's a place to start. Because if you get to a point where you can't find a derivative, then it's like, well, at least I have my discontinuities, So hopefully that's not often the case, but you never know. So derivative. Oh, and C and D on this interval. So 2 minus secant squared. Set it equal to 0. And you'll get secant squared x equals 2. We'll go from there in a minute. We'll talk about, just very briefly, the idea of it being undefined. Right? I mean, we can set it equal to 1 over 0 if we want, but the only place in which secant, that's 1 over cosine, so the only place in which the cosine is going to go to 0 would be at pi over 2 or negative pi over 2. So we're going to run into the same issue with the derivative that we had with the original function, where any instance in which it would be undefined is taken away by the fact that the domain is restricted. So if you neglected it, you get away with it. All right. If you showed the work, that's fine too. All right. So I'll show the work in a minute, but let's just carry this out. So secant plus or minus root 2. Reciprocal, because I you can figure it out. I mean, if you happen to know your unit circle well enough that you also know the reciprocal trig functions, good stuff. If not, find the reciprocal. If you don't recognize that as being the same as radical 2 over 2, rationalize the denominator. one thing I don't like about the unit circle. I don't like those radical 2 over 2s. You'll actually see in some textbooks they write it as, for the 45s, they write it as 1 over radical 2 instead of radical 2 over 2. Just because this usually comes up, this only comes up after you get this. So they're like, well, let's just make the unit circle have this so that I don't have to worry about trying to figure this out. Same thing with the tangents. Like tangent of 30 degrees, 1 over radical 3. And very simple, very easy to identify algebraically. Tangent of 60 degrees is radical 3, which is the reciprocal of that. It's a nice relationship. But if you rationalize the 30 degrees for tangent, you get radical 3 over 3. And that's not as convenient. So, you know, there's a case to be made that you kind of learn rationalizing denominators for nothing. I mean, it's not true because it's a valuable skill that helps, you know, solving algebraic problems. But it was oversold. It's like, you cannot have radicals in the bottom of a fraction. Yeah, you totally can have radicals in the bottom of a fraction. What's wrong with that? It's just they wanted you to learn the skill, right? That's why you did it so much and lost credit every time you didn't do it. All right, so within the appropriate domain, I need to indicate any x value for which cosine is equal to 1 over radical 2 or radical 2 over 2, positive or negative, but only in 4th quadrant, 1st quadrant. All right, so the 45-degree reference angles in either of those quadrants. So we're looking at negative pi over 4 and positive pi over 4. Seven pi over 4 is equivalent in terms of location, but it doesn't fall in the domain. So we gotta stay with that. And honestly, I think it's for these particular situations that you learned about coterminal angles back in Algebra 2. Where it's like, okay, you got 5 pi over 4. What's another way you can get to that? Okay, good. What's another way you can get to that using a negative angle? Good. You know, like it's why are we doing this so much? It's for stuff like this. All right, so that takes care of that. Just so you can see what it looks like. And actually, for me to quality control myself and make sure that I'm not making stuff up here, let's do 1 over 0 equals 2 minus secant squared x. If you want, I mean, in either of these two first steps, when you set it equal to 0, set it equal to 1 over 0, you can multiply through with the reciprocal just to get it at a secant form, but I don't see how that's absolutely critical. So if you were to put this together, well, at least in the first part, in this part, you kind of need to. So 2 minus 1 over cosine squared x, common denominator, 2 cosine squared x minus 1 over cosine squared x equals 1 over 0. And then cross multiply, you get cosine squared x equals 0. And that's where you see that it falls apart, that you'd never had to do all of that stuff anyway. All right, because the only place that cosine is going to be equal to 0 is at negative pi over 2 or pi over 2. But they're outside of our domain. All right. If these were square brackets, this would be a necessary calculation. But you'd still end up with the same result. You would go through the process and say, all right, I did all this stuff. Well, actually, you wouldn't have to do it here. At some point, you'd have to justify that even though there's square brackets, they don't contain real values. There's no graph there. Right? So the only way it would be phrased like that, or the only reason it would be phrased like that, would be for the purpose of a horrible trick question. You know, like why would they put square brackets on something that doesn't exist? And it's kind of a contradiction. I mean, it's definitely a contradiction. Anyway, we have our critical values. Now, I mean, because we are looking for concavity here, second derivative. sometimes you can make a determination because I don't think just intervals where it's concave down and concave up. Sometimes you can make an educated guess, your multiple choice question, based off of your extrema where the intervals of concavity would be, but it's the inflection point that we're really after, so it couldn't be, problematic. So the 2 would go away. It would be -2 secant x times the derivative of my inner function, which is secant x. So secant x becomes secant x tangent x. Crikey. Thanks, dude. All right, so you can clean it up if you need to. At this point, I think the better way to go, because we could leave it in secants and tangents, but if we put it in reciprocal form, it's going to make it a little bit nicer, because we're going to have 3 secants, or I'm sorry, 3 cosines that are going to go onto the bottom. 1 for each of the secants and then 1 for the tangent. The reason that's a good thing is because we're setting this equal to 0 in a second. So that's going to go away. All right. So by shunting it down to the bottom, we're basically saying, we don't need you. All right. So -2 times the sine of x would be on top. And that's what my second derivative would be equivalent to. So I'd set that equal to 0, which is the same as setting just the top equal to 0. So we're looking for any instance in which the sine function is equal to 0, because I just divide out the -2 in my mind, which is not difficult. So yeah, x would be equal to 0 on that interval. I mean, it could be pi, 2 pi, 30 pi, but 0 is the only one that's on the interval. So we got a new value to work with here to go along with the plus or minus pi over 4. So when we create our sign chart, we have x, -pi/2, excluded, to -pi/4. Stop, take a look around at -pi/4. -pi/4 to 0. Stop, take a look around at 0. 0 to pi/4. Stop, take a look around at pi/4. And then pi/4 on to pi/2. So we need f prime, double prime, triple prime, just kidding. Conclusion. Really terribly drawn lines, terrible, as they say. And now we dance. No, we don't. I'm wearing it backwards, so it's not going to work. So we have to evaluate. Having a sense of trigonometric functions is hugely important for this particular question. This is why we learned about unit circle. For this one question.
Awesome.
Here's pi/2. Here's -pi/2. Okay. And the whole purpose behind this is so that we do not have to do insane calculations. All right. So we just need signs. That's all we care about. Positive versus negative. So our benchmarks are at pi/4 and -pi/4, and well, also 0. All right. Everything's positive in the first quadrant. Only the cosine related stuff is going to be positive in the fourth quadrant. Okay, so going to my first derivative, we're looking at something positive being raised to the second power. All right, because secant is cosine related, so regardless of whether it's in the fourth quadrant or in the first quadrant, it's going to give you a positive quantity. It's also being squared, so you have the added bonus of not really having to worry about that. So we're taking 2 and subtracting from it some positive number. But we also want to be thinking about what could be the quality of those positive numbers, all right? So the largest possible positive number that can happen on that interval is really what we're focused on. So we're looking at negative pi over 2 to pi over 4. So if you want, you can pick a value, like for example, 5 pi over 3. Well, the equivalent in this case would be negative pi over 3. And you could plug it in. It's not an unreasonable calculation. If I were to do that, the secant would be the reciprocal of cosine. Cosine at negative pi over 3 would be what? For cosine, it's rad 3 over 2, rad 2 over 2, and then 1/2. All right? So this is going to be a quarter for cosine, right? If we did it, we took it and squared it. All right? So 2 minus 4 is going to give you a negative 2. All right? So a negative number. But we want to start thinking about the quality of the numbers rather than the quantity of the numbers. So we want to get into the idea of what would be the size relationship as you get further and further away from the x-axis related to the secant function, because that's going to give you a sense of what's going on. For example, I know from experience that once I get to the pi over 4, that's when secant squared is going to be equal to 2. And that's because secant itself is equal to radical 2. And if I square it, you get a 2. It's only going to get bigger from there on out, right? So bigger numbers, bigger than 2 for secant squared here, smaller than 2 here, all right? Smaller than 2, bigger than 2. So you can make those determinations just based on knowing the quality of the number. We'll pick up with this tomorrow. But something to think about definitely was dependent on your knowledge of trig graphs. Just like for polynomial functions, it gets a lot easier if you know what a cubic and quartic function looks like. This stuff gets a lot easier if you know what a trig function looks like, particular trig functions. Obviously more complicated, all right? But when we're looking at our unit circle, in the appropriate domain, we just discovered that the benchmarks would be pi over 4 and negative pi over 4. All right, because we can make the assumption that the same would be true in the opposite direction. All right, so any value that is occurring prior to pi over 4 would square to be a number less than 2, therefore giving us a positive result. All right, so if we're thinking in terms of our derivative, it would be positive in these neighborhoods, negative in these neighborhoods. All right. That's the intuition behind it. You could always fall back on doing rote substitution. The problem is, if you've been overly reliant on a calculator for trig, what's it going to do for you? Because you could know that I have to plug in like a pi over 6, but if you don't know what that's going to give you, then cool. You know, it's not going to be of much benefit. You know, and if you don't know what this graph looks like, I don't know what it looks like. I know it has some aspects of linearity and also a tangent component to it. So it's probably a somewhat straightened out version of a tangent function. But that's my best guess. I wouldn't really know until I graphed it. So you can't rely on the shape of this to help you fill out your sign chart like you would with a polynomial function. All right. So as I'm working my way from negative pi over 2 to pi over 2, I'm looking at negative, positive, positive, negative. All right. But the good news is we can use, to some extent, I'm going to make this red, our answers for the first derivative in the sign chart to help us figure out our second derivative. All right, because assuming you don't have asymptote, if it's continuous along the interval, we know that we're dealing with decreasing followed by increasing, right? So decreasing followed by increasing would be a relative min and a lag, apparently. I gotta write like super slow now. It can't keep up with my brilliance. So decrease, increase, increase, decrease. All right, so increase to increase, that's no change, but increase to decrease would imply a relative max. All right, so you might think in terms of a polynomial function. I tend to default to polynomial function shapes. You know, smooth curves that when you have a turning point, it looks somewhat parabolic. You know, when I think quartic function, I think of the best case scenario, something like this. I tend not to think of something like this. You know, even though this would, the second one would technically be a quartic function, you know, it's, I mean, a shaky quartic function, obviously. But it would still be, it would still satisfy the definition. So here I would be thinking that decreasing and increasing. All right, so in this case, I'd be decreasing, then increasing, then decreasing eventually. Anyway, so we were suspecting that there would be a point of inflection at 0. That's our possible point of inflection. We solved for that. If the graph looks something like this, then that's a logical assumption to make, right? Because there is a transition of concavity. The second derivative test is what's going to help us here, right? Or at least the intuition behind the second derivative test. Because if there is a relative minimum in a continuous differentiable function, if there's a relative minimum, it must occur on an interval that is concave up. All right, so that's telling me, without doing any calculation in my second derivative, which is more intimidating than our first derivative, it's telling us that our second derivative sign must be positive because it has to be concave up. All right, surrounding the relative max, it must be concave down. That's the only way that you could have an interval containing a max if it's a continuous differentiable function. That's why we test for continuity. All right, so this would be a concave down situation, which would imply meh and meh. All right, so two negative signs in my second derivative. All right. Since there would be a change in concavity around 0, that allows for us to conclude that we're looking at a point of inflection. All right, but it comes down to continuity and differentiability on the interval. All right, because if there were any asymptotes along the way, game over. All right, but since we know that the only asymptotes happen at the endpoints, negative pi over 2 and pi over 2, we don't have to worry about it on the interval. All right, so those little calculus recognitions make all the difference because, again, I mentioned this with the polynomial stuff. The one thing that you shouldn't be doing, very often anyway, you resort to this. It's a last resort. You know, like in case of emergency, break open glass, that kind of thing. You should not be plugging in numbers into your first and second derivative. All right, it takes too long. So it's the intuition behind this that's going to get us our solutions efficiently. All right. I mean, because I can only imagine. You know, you're sitting there in the AP, you get to the part where you have to make a sign chart. You've done all this work already. You're like, you're gonna spend the next half hour just making the sign chart. Skip. You know, like what are you gonna do? You're gonna waste your time on it. It's not worth it. All right, so you think about the nature of the graph. Think about the nature of increasing and decreasing versus concavity, relative extrema versus concavity. And then that should lead you to your appropriate conclusion. Let's see, find intervals where the function is concave up, down, identify extrema, check, check, and check. Boom. All right, so obviously the trig stuff is where it starts getting a little funky.